next speaker, who is Sunil Mohanlal from the Laboratoire d'Hydraulique Saint-Venant. Sunil, are you here?
Yep, sure, I hear. Let me share my screen now.
Yes, please. Yes. Excellent. Okay.
Right, let me know when to start.
I think you can start, so please go ahead.
Okay, hello everyone. I'm Sunil Mohanlal, a PhD student at Laboratoire d'Hydraulique Saint-Venant, and I'll be talking about depth-limited wave breaking dissipation in a potential flow model, working with Marissa Yates and Jeffrey Harris. So just a brief overview. So our work funded by Energy for Climate aims in looking at an improved modeling of nonlinear wave field, for example, here region 1, and in the presence of wave breaking, that is region 2 here, and then estimation of wave forces and structures about region 3 here, and an experimental campaign on these. And as part of my first objective, we are looking at modeling side-scale wave field, which would also include the effects of wave breaking. And since computational costs for running simulations of irregular waves over large times are high, and as we're not interested in small-scale effects, an optimal model will be a potential flow model, but it would not account for any dissipation mechanisms, but we can externally add it over a prescribed region in space and time and a prescribed strength. And my following talk would be revolving around this concept. So the motivation is that so there's a unified breaking criterion that is proposed by Direct et al. 2020, and we want to see how this works well with a validated dissipation model called hydraulic jump for triplet limited wave breakings. And the same way onset criterion is used to parameterize something called the breaking strength for stripless limited waves as shown in the figure here. And we want to see how this kind of parameterization behaves for an hydraulic jump model. And so the numerical model we're working on is called a fully nonlinear potential flow model. So here the flow is described by a scalar potential field, and such that the velocity, the Laplacian of the potential is 0 in the domain, and for the boundary conditions, it's bounded by two conditions on the free surface, one signifying no flow across the interface, and the other one's the constant pressure Bernoulli equation. And then we have our bathymetry as an impermeable one for the test case that I'm working on, and then the lateral boundaries could be the Dirichlet, Newman, or periodic. And an overview of how this model works is that you know the velocity potential and phi at the velocity potential and free surface elevation at a known location at a given time. And with that and all the other boundary conditions, you solve for del square equal to phi in the domain and obtain del phi at the free surface. And with this, you calculate the quantities of the rate of change of eta and phi again at the free surface, and then march in time with a suitable time scheme. And so the FNPF model that I'm working on right now is called the Mystic model, where phi is the velocity potential phi is resolved into vertical and the horizontal component. And then spectral approach is used for a vertical, so that the vertical coordinate is mapped into a strip of S varying from -1 at the bottom and +1 at the free surface. Then the phi along the vertical is approximated by a Chebyshev polynomial up to an order of NT that we see here. And then we calculate the vertical velocity on the free surface by dou phi dou S at S is equal to 1. And then the kinematic and the dynamic free surface boundary conditions are reformulated in terms of this W tilde and the other free surface quantities. And with this, we march in time to obtain quantities at the next time step, and then we repeat the step, the process. And for wave breaking, we apply a damping pressure called the P surf, which would account for wave breaking, and it is externally specified over a specific region in space and time, which we will look at in the following slides. And we'll just look at a few definitions quickly. So an accurate estimation of like local wave quantities, such as this wave celerity, is a crucial thing for the study that I'm making, and because it will be useful in the type of breaking onset that I'll be looking at, and also when parameterizing the breaking strength. And for this, I use the definition from for C given in Stencil 2002, where the Hilbert transform in space of the free surface is calculated, which would essentially give a negative pi/2 phase shift of the input wave, and with which a local phase function theta is calculated. And then with the higher order finite difference formula, we calculate the local wave number. And with this, with this local wave number and the linear dispersion relation, we calculate the celerity. And then we calculate the wave period by the simple formula C equals to omega by k, and then we rearrange it. And for the breaking onset, a quantity B is defined as the ratio of the maximum the horizontal velocity at the front face of the crust and the wave celerity at the crust. And these are shown here in the figure. And in Dirac et al. 2020, they show that this parameter B equals to 0.85 separates the breaking and the non-breaking crust. And what we do is we employ this definition and let the model apply wave breaking when an evolving crust, as you see here, exceeds B equals to 0.85, and we do not, let's note this point as X star P star. And so you see here the way the wave crust evolves, and then this is the point at which we say okay, now you can start applying a wave breaking. And then we just define a parameter here called gamma, a breaking strength at the onset, as defined in the Dirac 2018. It is calculated and it will be used later to parameterize the breaking strength. And this parameter gamma is equal to a wave period times the rate of change of B. And for this, to calculate this rate of change of B, we calculate this evolution of crust through time, as shown here in this figure. And the point at which 0.85 we get 0.85 is identified, and then what we do is take a linear fit at a couple of points preceding this, typically in the range 0.82 to 0.86 to calculate this dB by dt, and then the dB is defined as the wave period at the onset x star t star. And as soon as we identify the onset, an instantaneous power that should be dissipated is calculated, which is proportional to that of an hydraulic jump. And this proportionality constant, mu naught, is taken to be 1.5 following Swenson et al., who calibrated this for spilling breakers. And this is also later shown by Steve 1984 that it could be extended to 2 depending on the test case. And on the top figure, you see the kind of parameters, mainly the wave heights and the depths that are required to calculate this instantaneous power. And then following Grilly et al., what we do is this instantaneous power is distributed as a damping pressure around the breaking crust in the region XL XR that is proportional to that of the normal velocity. And then so wave breaking is turned off at 0.3, and there isn't much information about this, and we iteratively selected this by comparing simulation data with a few experiments in the region far ahead of the breaking waves, and we will look at that when we look at results. And so on the figure left here, you see the kind of variation of this quantity pi, the dissipated power in time from the onset. So from the onset, so when you identify onset, you start applying this damping power, and then you track the evolution of this damping power up to when B here reaches 0.3, and then we have offset here, and then from this we calculate a time averaged power, and then this is nothing but it signifies like a dissipation rate per unit length of the breaking crust, and an average value of that. And then so that's we call that, let's call that as pi bar, and then in analogy to Duncan 1983, we calculate a quantity B called B, which is equal to this pi bar times G divided by CB to the 5. And CB is the wave celerity calculated at the breaking onset at the point at which this U over C was 0.85. So results, so we'll first look at prediction of onset of breaking waves with experiments, and then we'll see the accuracy of calculation of this wave celerity with the formula that we just saw, and then compare a set of test cases to check the validity of the dissipation model, and finally look at the parameterizing of the dissipation strength with the breaking strength. And so among the test cases that we're looking at are Bijibach's 1993 spilling and plunging, regular and irregular waves, and the 2 strongly nonlinear test cases, Tinker V94 and Hansen-Swensen's 1979. And so these are all generated at about intermediate depths, and then intermediate relative depths, and then travel towards shallower conditions. And so we see that with the onset criterion of U over C 0.85, the onset is always predicted a little earlier than that in the experiments. And so this may be because we chose the onset at U over C equal to 0.85 than the more classic U over C equal to 1. And we can't use U over C equal to 1 in our model because it's too late, and the wave height grows very quickly at this point, and the dissipation is not quick enough, and the solution would stop. So maybe U over C equal to 0.5, like a safe lower bound to predict an onset. And here we compare the wave celerity calculated with the partial Hilbert transform that we saw earlier for a strongly nonlinear test case from Hansen-Swensen. And here you see the bathymetry of the same. And so we see that the wave celerity obtained from this method agrees well with the experiments. The experimental data was provided by Stefan Grilli, and so this method of calculation of wave celerity also captured this effect of slight increase in wave celerity after the onset. So that's seen here in the experiments, and again, as the onset is identified a little earlier, so we see this increase here, and then there is clearly a difference seen with the shallow water speed and what we calculated with Hilbert transform. And so here we look at we'll look at the free surface elevation of Beji-Bunch's spilling test case. So on the top, you see the kind of bathymetry we have, and this is called the generation zone on which the desired progressive wave is imposed. And here you have absorption zone where the waves are absorbed. And on the top, you see the gauge locations whose time series are shown below. And overall, there's a good agreement. And so wave breaking is seen in about from 12 to 14 meters. And so observing these free surface elevations after these gauges helps us in determining what kind of the termination criterion that we want to look. And like I said earlier, we selected that u was equal to 0.3 to terminate iteratively by looking at values at these gauges from this test case and the other test cases that follow. And this is a similar test case like earlier, but with a larger wave height and the plunging breaker. And again, we see an overall same results in this case as well. And then here we look at two similar irregular test cases, one with a significant wave height of 0.042 meters, so that's a spilling one, and then 0.052 meters for a plunging one. And at the bottom, you see the evolution of these significant wave heights and some statistical quantities defining the nonlinearity and the shape of the wave across the domain. And so the results are about for 15 minutes of wave propagation. And so we see that the significant wave height at 12 to 14 is good in both the cases here. So the onset's working fine. And we see that the offset criterion, that's about, so with the wave breaking ends here. So we see the values of significant wave height at these gauges at 16, 17, at like far after the offset of wave breaking, and even these are agreeing well. So the offset criterion is working well. And the dissipation model is calibrated for spilling breakers, but we see fairly accurate results for plunging breakers as well for this one and the earlier one we saw. And then this is another case called Team Kirby from 94 spilling one. And and in the experiment here, but we see wave starts to break it after this location about 10.25, but in our model, the onset is identified like a little after this one. So you see the wave height starts to decrease. But whereas in the experiment, it still remains constant and it starts to decrease after this point. So that's why we sometimes have these kind of dissimilarities at the vicinity of the onset. So finally, for all the test cases, we saw the breaking strength gamma and the dissipation strength B is calculated and plotted here, along with the analytical curve that is given in Deducti 2018. And so the solid dots here are for regular cases, and the hollow ones are for irregular cases. And the color blue are the spilling ones, and the red are plunging ones. And the horizontal line you see here in between the dots they represent about 1 standard deviation on either side, computed with about 30 data points. And this is the curve from the AGU poster of Deducti et al. 2018, and we suggest that a max value of B is something like 0.02 for shallow water waves, and whereas the way we define B, we get the value of something like in the range of 0.03 to 0.09, and gamma in the range about 0.4 to 1.7. Okay, all right. So to conclude, so we saw onset 0.85. It works well for depth limited breaking, but it might underpredict this wave elevation at the onset or around the onset. And the hydraulic jump model works well for depth limited breakings for a series of test cases that we saw. And even though this constant mu naught equal to 1 is first calibrated for spilling breakers, and we tested it for just a couple of plunging breakers, so one from regular and irregular one, but they both seem to give pretty accurate results. And finally, so we see that the magnitude of B was in the same order, and these are our actually latest results, and we're looking for reasons why this B would be in this same order. We know this is dependent on this instantaneous power, which is mainly dependent on height, so maybe there is some clue here. And to look at this in more detail, we'll be looking next at steepness limited braking and maybe get an experimental measure to calculate what kind of B values we would get there. Yeah, that's it. Thank you very much for listening.
Okay, thank you. Thank you for your talk. There's plenty of time for questions. So are there any in the audience? Okay, so maybe I have one. So can you tell us a little bit more about the implementation? So you need the phase speed. So you need C. Yeah. So how do you actually have implemented that?
You mean how have I calculated the C?
Yes. So yes.
Okay, so there are two ways. So if you look at the formula here.
Il y a un facteur qui va parler juste après en parlant de individual wave run-up.
Okay. Yeah, please go ahead.
Sorry. So there are. So I just tested two methods. So first way is okay. So essentially, the most nonlinear one is if you can define the local wave number and the local the wave period, both in terms of Hilbert transform, one from space and time. But in time is not possible because you don't have the time series elevations after braking. So what we do is we just do half, like a partial Hilbert transform. So we do only in space and then use the linear wave speed. And then to calculate this partial Hilbert transform in space, you could use FFT to calculate this, or what I've done right now is just calculate this by just the integral here. And this by just the integral would give fairly good results compared to what you'd get in FFT. And yeah.
But so my question is, so the Hilbert transform, this is non-local, right? So when you do wave by wave analysis, I suppose that you have to be able to track a single wave. So how does that work in practice?
Yeah, so exactly. So if you see here, so for example, if I identify this crust, so at this crust I calculate at this crust at the peak point, I calculate the wave celerity that was locally defined by the previous formula, and then I track this in time. So for example, I look at the next time step and then see where the crust and again I calculate it, and then I kind of follow this through.
Yeah. So the Hilbert transform is it's from X to X. Okay. Okay. Fine. Okay.
Can I make a comment? So actually, the velocity that it is in the B coefficient is not the phase speed, but it is the crest speed. So in an unsteady wave, a crest speed is different than the phase speed. So I mean, I understand that your implementation is a practical implementation now to get an estimate, but ideally you should do the tracking of the crest location and then estimate the crest speed. But I guess that would be very numerically challenging, is right? It would slow down everything.
Yeah, it would be challenging, but there's another way to look at it. So, for example, so we say, or the paper here, the 2020 says B is equal to 0.35. It separates the braking and the non-braking crust, and then they just define U as the velocity, the horizontal velocity at the crust. And what I've taken here is the velocity at the front face of the crust. So you see there is some liberty. And again, when Michael Banner talked on the day before yesterday, he gave this value as 0.855. So there is some ambiguity in the last digit. So if you look at the figure again here, so what I've done here, the resolution in time is about the wave period over 150, I guess. And so you see it only took like 3 time steps to reach from 0.8 to 0.85. And so even if there are some dissimilarities or some differences in the way you define U, it would hardly make a difference of maybe 1 or 2 time steps. So strictly numerically speaking, I mean, there should not be that much change in the results.
Have you done one computation by computing the exact crest speed and see what is the difference with the Hilbert transform approach, even as a test, even to check how good is, how much are the differences? I mean, I understand your argument. For a practical do the Hilbert transform, but I wonder if if in future it is feasible now to do the the tracking of the crest.
Well, actually, I might have made a test before, but right now I think I don't have a quantitative answer for this, but something I may look in the next future, maybe.
Okay, thank you.
Thank you.
Yeah. May I ask a question? Yeah, Mario. Please.
Yeah, please.
Yeah. Did you consider wave setup or set down, and did you compare with measurement or for the experiments you showed us? To get,
no, the experimental results are just one that are taken online. I'll be doing experimental results next. So far, I have not done any yet. No.
So you did not look at wave setup after breaking?
No.
Okay, thanks.
Just as a comment by Syed Hamad Hassan, who says that he also observes the same phenomenon, that the way in which U over C rises very fast, and that he implemented almost the same model in his thesis.